Good afternoon, everyone. My name's John. Welcome to today's Journal Club. I'm very excited to say that we have a special guest today, Dr. Alexander Edwards. Um, Alex, your first time presenting on Journal Club. How are you feeling?
Yeah, no, I'm excited for a discussion.
Good. Well, I think it's going to be really great today. So the topic for Journal Club today is how effective is natural ventilation in preventing the spread of respiratory infection? And this is based on one of Alex's papers recently published in the Journal of Hospital Infection. Of course, ventilation in healthcare has been a huge, big theme through the pandemic. I know there's been a lot of the data come through, so I'm looking forward to Alex summarizing some of that for us with a focus on natural ventilation. But just before we hand over to Alex, couple of bits from me around what we're trying to achieve with our journal club. So the main aim really is to provide insight into a topical paper, something that people want to talk about. We're always open to suggestions, by the way. If anybody has a good paper that they think they'd like to see presented or present themselves, do please get in touch with us. We're keen to generate discussion. It's always the discussion at the end of the journal club that's my favorite part. It's an opportunity for CPD, for all of us. We're keen to create opportunities to exercise critical thinking. So not just read the paper as written, but to think about as much what isn't there as much as what is there. To build confidence so that we can all be independent in our research and study, to build and foster a network of enthusiasts, and ideally have a little bit of fun as well. Just to let you know, IPC Journal Clubs are recorded and made available online after the event. So, without further ado, I'll hand over to Alex to talk to us about natural ventilation. Alex.
Thanks, John. Yeah, no, thanks. Thanks for the invite. Really pleased to be here talking about my recent study. Although it doesn't seem so recent anymore, time flies really quickly. I'm going to just throw up some slides. And as it's one of my own papers, it's given me a bit of freedom to talk a little bit more about results and hopefully summarize some of these and maybe feed in some discussion points for later as we go on. So I titled this The Importance of Ventilation, and as John said, this is, the focus of this study was natural ventilation, so it focuses on a naturally ventilated hospital ward from Leeds teaching hospitals. So yeah, let's dive in and see how we get on. So some motivations really. I suppose this audience is very familiar with these kind of things, but I think it's always important just to re-emphasize why we do such studies. The COVID-19 pandemic highlighted the importance of airborne transmission for us, but this is an infection route for many other pathogens as well. And we see that this can be important for different pathogens that may not be originally airborne, but maybe aerosolized through different hospital processes or from surfaces and things like that as well. So it is an important transmission route. I should also mention that when this work was done, the definition of airborne transmission was slightly different, and some of you may be aware that the World Health Organization changed the definition of kind of airborne transmission, moving away from this dichotomy of different particle sizes. I suppose this kind of aerosol versus droplet argument, and thinking that any particle that travels through the air and is inhaled by another individual, regardless of size or distance, is classed as airborne transmission, and renaming them this infectious respiratory particles. But this work very much focuses on what I would view as long-range airborne transmission, so thinking about the smaller particles, kind of less than 5 to 10 microns in diameter, but thinking about this from a multi-zonal perspective rather than kind of close contact and in-room. And the reason for this work as well, and what this will focus on, is natural ventilation is heavily relied on as the main source of airflow in many hospitals. However, many hospitals fail to comply with this guidance and of 6 air changes per hour. So the next slide, I'll just have a look at this guidance itself. So this is from the HTMO3 guidance, so Health Technical Memorandum. Ventilation guidance says that there's a preference for kind of natural ventilation in hospital wards. We're kind of focusing, not sure how well you can see my cursor on the screen, but focusing on general ward, patient ward hospitals having that recommended guidance of 6 air changes per hour. So there was an update to the health guidance in 2021. This put a bit more of a stronger requirement on inspection and audit, and introduced a ventilation safety group. So I suppose these changes were prompted by the COVID pandemic. But I think there still remains a big challenge with how we deal with some of this guidance with historical spaces. How do we get these spaces to comply? And one of the things hopefully we can discuss a bit later as well is how we try and get this compliance whilst combating other guidance that's in place, such as privacy, safety, addition of partitions and things like that. And obviously many of these hospitals still don't comply, so it is still a big challenge. I wanted to be sure of the kind of background of the audience, so I thought I'd just include a couple of slides of what I kind of view natural ventilation to be. I won't go into too much detail, but just to kind of help us visualize what we're actually talking about when we say natural ventilation. It's kind of made up of two different types of airflow. And they often come with different names. So this one, for example, wind-driven flow, sometimes called cross ventilation or cross flow, essentially is driven by pressure differences. And so what happens is you get this airflow that flows to the facade of a building, and it's driven by low pressure at the opposite side of the building. So you've got high pressure on the side where the wind is blowing and low pressure on the other side. And so that air wants to go to that low pressure region. So pressure wants to balance out. And so that's what happens if we have these two openings. So you can see on the picture in the bottom that we've got these windows on either side, then you get that cross ventilation, the air gets pulled through. And the best way I can kind of help us visualize that is if you think of the summer when you've got your patio doors open, and then you might open the front door to go out to the bins or something, and then your living room or kitchen door will slam shut. And that's kind of a representation of that cross flow ventilation. The other kind of ventilation is called stack-driven flow, sometimes buoyancy-driven flow, sometimes temperature-driven flow, and essentially this is driven by temperature effects. And so this kind of works on the basis that outdoor air is typically cooler than indoor air. And so what happens is you get that cold air that comes into a building, it warms up gradually and hot air rises because it's less dense than cool air, and then that exits at a higher point. So here there's a couple of different examples of openings high up in the ceiling, but sash windows are also a nice example because you get that kind of localized stack effect with the top and bottom opening. And then I wanted to share this picture to the audience as well, because I quite like this picture. This is from a hospital in London, 1910, but I think it really quite nicely represents both forms of these ventilation. You've got these huge sash windows that are open both top and bottom on either side of the building, so they've got that localized stack-driven flow, but then you've also got the wind-driven flow across the ward as well. And I think this is probably quite a nice discussion point for this topic, because we think about Nightingale style wards, we think about 1910, this hospital ward. They didn't have the airflow modeling tools that we have today as engineers, and so I think it's really interesting that actually ventilation and airflow on these wards were driven by how people feel and how well people healed in these hospital environments. But I think that's probably a good metric for indoor air quality that we fail to account for these days as much as we should. So that's kind of an overview of natural ventilation. So I'll dive straight into the paper and that we're discussing today and some of the results and see where we get. So this study is based on a subset of a respiratory ward at St James's Hospital in Leeds. So it's an adult respiratory ward. It's much bigger than the geometry that I'm showing on the screen now, but we kind of have to start somewhere from a modeling point of view. So motivations for this were behind obviously selecting 12 zones that are representative of a hospital scenario. So I think this geometry represents kind of typical hospital ward layout quite well. So you've got these big bays where you'd have maybe 4 patients in them on either side. Then we've got a kind of nurses station, reception area, drug preparation area that typically exists in most wards. And then some single rooms with maybe an ensuite behind. And then on the opposite side of the room, you've got this long connecting corridor to some of these clinical rooms or staff rooms or other things like that. And so what we did behind this study was we were interested in seeing how these transient airflows, in particular the effects of transient weather conditions, external weather conditions, how these played a role in the airflow and natural ventilation on these spaces. And so we kept everything else fixed. It was important that we didn't allow occupants to move or change any of the internal settings of the hospital. We just wanted to see the effects that we got when we changed the weather conditions outside and how that consequently affected the indoor airflow inside. So having said that, the doors were closed for the full duration, and the windows were open for the full duration. And we ran the simulation for a period of 6 months, which I think showed the power of a modeling tool quite well, because I ran that on my local machine. It didn't take more than 30 minutes. But I think obviously 6 months is unrealistic in terms of an infectious person being present. They'd have to be very ill to be ill for an infectious for a period of 6 months. But I want to kind of emphasize that, think of this as a kind of tracer, or putting a dye into a flow. By putting an infectious person in there for a 6-month period, we're able to kind of track that contaminant and see how that moves through the space. And see what happens to some of the concentration values. It gives us a better idea of some of these different behaviors that we expect to see. And what we did see when we ran the scenario, so we ran an airflow simulation with the transient weather conditions and natural ventilation, and then we had this infectious person present. We saw that we got these really sharp spikes and peaks in infectious material. So this plot is kind of representing, I suppose, infectious pathogens in the air moving around these different zones. So the infectious person was in zone 5 in the nurses station in this scenario. So you can see that that's the zone with the highest infection risk. But what you can see across all the other zones as well is that we get these really sharp spikes and uncertain spikes in infectious quantum concentration. And actually this is suggesting that particular days, particular weeks, particular months are riskier than others, purely driven by these external weather effects. And what I've put here on the left hand side is just some kind of summary statistics, just thinking about the different levels that we've got. So again, I'm not sure if you can see my cursor, but thinking of the 0.5 on the y-axis, we can, if we imagine drawing a line across there, then only 5% of those concentration values are above that point. And then if we go up to the 1.5, then only 0.35% of concentration values are above that point. So hopefully that just emphasizes to you that although they look like the dominant feature of this plot, they're not. They are infrequent, but actually this is what's driving our infection risk on this ward. And this is, as I said, because we kept everything else the same, this is purely driven by these transient weather effects and airflow. I just realized, by the way, I'm looking at the slides on a second screen. I'm not looking away from the main screen here. So some of the results to summarize, obviously, like I say, 6 months for an infected person is a bit unrealistic. So to assess risk on this zone, we actually stripped this down to a weekly period. And so what we did was we split the 6-month period up into single 7-day periods, and then we take a kind of average over that. So it allows us to kind of quantify a typical week on that hospital ward, what kind of behavior we would expect, but also hopefully capture some of those discrepancies between the different weeks as well, which is what we're seeing here in the probability distribution. So again, I'm not going to dive too much into the numbers here, but the main thing I wanted to highlight from this image is actually the large spread of the data. So you can see we're ranging from kind of 4 possible exposures all the way up to 12 exposures. So if we're thinking about this as a population percentage of the hospital ward who's going to be exposed, that's basically saying that some weeks we might get 25% of the population exposed, and other weeks we might get 75% of the population exposed. And so hopefully this starts to demonstrate the uncertainty that natural ventilation and relying on this form of ventilation can cause on some of these hospital wards. And of course, this is before any other infection risk takes place on this space. So of course, these are just predictions, these are model predictions, but it gives an insight into kind of that uncertainty of natural ventilation. I wanted to share this slide with you all because this was something that we developed as part of this work, and we thought it could actually be quite useful thinking about future applications and impact to healthcare, but actually how do we visualize some of these quantitative results so that they're useful for healthcare workers and clinicians and estates managers and people thinking about building design in the future. And so we came up with this kind of heat map tool that gave us a risk index for each particular zone, so we could actually assess on a given day or a given week what the risk to a particular zone might look like just based on these weather conditions and where that infectious person might be. And so again, open to discussion about this. I'd be be keen to hear what you think would be useful, but thinking about whether we could get a heat map like this on a base station or on an iPad for a healthcare worker, and thinking about running some different scenarios. So maybe there's an input where a healthcare worker could, say how infectious they think somebody might be based on symptoms, or where the infectious person they suspect is, or what the weather conditions are like on a particular day. And this might give us an idea over patient location. So again, we might think about moving an infectious person to a different space to isolate them better, or we might think more about actually moving some of the particularly vulnerable patients to different spaces as well. Or obviously it gives us an idea of where to put maybe localized mitigation strategies. So you might want to mask up for particular zones, or you might want to input some air cleaners or things like that into particular zones as these situations arise. I think another thing that motivated us to do this, which is what we describe in the paper, is also thinking about the pandemic and thinking about those resources not being so available, and actually a tool such as this could tell us, in this case obviously it's quite high risk, but in other cases it might tell us that only certain zones are high risk rather than the ward as a whole, and so we might be able to save some resources and only apply them to the zones that need them most. So thinking about the actual natural ventilation then that they're predicting from the model in this ward. So the plot on the left is showing a probability distribution of the ventilation rates across this 6-month period that we're achieving across the whole ward. And hopefully this highlights just how far away we are from that recommended guidance. So you can see the green line on the right hand side showing that 6 air changes per hour recommended guidance from the HTMO3, and then a probability distribution being miles off that with an average of about 0.61 air changes per hour. So again, we're really achieving quite poor ventilation rates, predicting poor ventilation rates on this hospital ward when relying on weather conditions. And this is with the windows open as well. The other thing I would say, I'm sure, again, I don't have to explain this to people who work in healthcare, but as you know, open windows in healthcare doesn't mean those big sash windows that I showed in the Nightingale ward. Open windows typically means about 100 mil of a sash window at the bottom that's then been glued at the top. So these are very limited opening that we have available, but actually, interestingly, we're relying on that as our main source of airflow. And you can see this heat map again featuring here on the right. You can see that actually we've tried to demonstrate some of those average ventilation rates for each individual zone. And so again, this might be useful in giving an insight into some of the airflow patterns or which zones might benefit from better ventilation. You can see that not always the average ventilation is achieved across all of the zones equally, which again is another uncertainty with natural ventilation. So what can we do? So one of the things we did in the study was look at the effect of if we had 3 air changes mechanical ventilation. Now this might refer to a kind of retrofitted building that has these vent systems in place, but it might also be equivalent of those 3 air changes per hour in the form of another mitigation strategy. But what we see when we put mechanical ventilation in as well as a natural ventilation is a drastic reduction in risk. So over 85% reduction in that risk index. And again, looking at that probability distribution, you can start to see that actually we've stripped a lot of that uncertainty out as well. We now know a little bit more about how many infections we're going to get and where they're going to be. And so that can help us to mitigate against some of these. And again, using this heat map here to demonstrate, this is a good example of showing that actually you might want to just put masks on when you enter zone 10, or put an additional mitigation strategy in zone 10 rather than as a ward as a whole. So if you've got a state of pandemic and limited resources, then that could be particularly useful in that case as well. What I think is interesting to highlight about adding this mechanical ventilation, this is this plot again here of average ventilation rates, but this time with the 3 air changes per hour mechanical ventilation. You can see that we're still not hitting that recommended guidance of 6 air changes per hour. And I think that's really important to highlight because we've still seen an 85% reduction in risk. So actually we've seen a huge chunk of that risk reduction without meeting that recommended guidance. And so I want to use this slide as a message to say something is better than nothing, and actually implementing what we can where we can, regardless as if we actually meet that guidance, that it can make a difference. I think sometimes there can be a bit of resistance of not making change in case we don't hit that recommended guidance, but actually some ventilation, additional ventilation is better than nothing. And then the final slide that I wanted to highlight, this is in the paper as well, and we did this as a bit of an illustration really, was to run the scenario again, but with all of the doors and all of the windows open this time. And actually what we see is kind of mimicking that fully open bay hospital with no partitions, and kind of mimicking something like those Nightingale style wards that I showed at the beginning. And actually we see that this is the lowest risk scenario out of all of the cases that we've run. We've got the lowest uncertainty. We now know even more about where our exposure is going to happen. Only 0 or 1 possible exposures now. Lowest risk index out of all of the scenarios. And actually, when we looked at the ventilation rate for this scenario, we achieved up to 48 air changes per hour in particular zones. And so I think what I wanted to show here, and possibly, this could lead into a discussion later as well, but is thinking about ventilation and the guidance that we've been given is if possibly effective for the way that these hospital wards were originally designed. When they were originally designed, natural ventilation probably was the most efficient type of ventilation, where we had fully open windows and fully open bays, and we allowed for that cross flow across these hospital wards. But actually, in reality now, we've had doors added to patient rooms for safety, security, privacy. As I mentioned earlier, the windows have been closed up again for safety and security. A lot of the openings to outdoor ambient environments have been sealed up, sometimes for energy efficiency, but again, that kind of safety security message. And so we've moved guidance on in terms of other aspects of hospitals, but that hasn't worked in tandem with the ventilation guidance. And so we're still recommending a preference for natural ventilation, but perhaps the hospitals aren't set up as well for natural ventilation these days as they were originally intended to be. So I think there needs to be a bit of consideration there for how we ventilate our spaces, or certainly the guidance behind that. And so that brings me to the end, really. Hopefully, I've not gone on for too long, and I've summarized the results. But I think when I was thinking about the key take-home messages from this paper, and when we did this work originally, the main message for me was just airborne transmission is complex. It's something that's often overlooked, and I think the COVID-19 pandemic really brought it to light. But it is a complex thing. It has a lot of different factors involved, and here we're just highlighting one of them, just this potential for natural ventilation and weather conditions outside. But it's highly driven by these transient effects that we get on particular days and particular weeks, and we've seen that risk can vary so significantly as well, which I think is a real concern. I mean, when we think about hospital appointments and visiting patients in hospitals, we don't think to check the weather, but actually you could be 3 times as likely to have a higher risk of infection than if you went the week after, for example. And again, thinking about staff and patients who are in these environments continuously, they don't get that choice over some of those natural phenomena, things that we can't control. We've seen that this is reduced when applying mechanical ventilation, and that overall message that something is better than nothing, I think that's really important. But I think, yeah, natural ventilation typically from our model predictions falls far below that recommended standard. But I think even more generally, we think about the guidance for natural ventilation, see how other guidance has moved on and perhaps starts to actually inhibit some of that natural ventilation that we achieve. And just showing again that natural ventilation can be effective when used as originally intended, but we have to ask the questions of whether our hospital wards are set up for that environment now. So considering some of these features for future retrofit of hospitals, future building design, but then that also poses the question of what we do in the meantime with our hospitals that are in situ. So that's me. Just a few acknowledgements here. This work came from a lot of different people as well who've fed into this and made this possible. Big thanks to Leeds Teaching Hospital Trust, who let me go and walk around this hospital ward many times with my tape measure to make sure that my models were as realistic as they could be. So we really appreciate that support, and obviously hopefully moving towards kind of the effects on IPC and making this environment a better place for us all. So yeah, that's me. So thank you. I will hand back to Jon.
Fantastic. Thanks, Alex. I mean, I found that really fascinating, and I've got tons of questions. Do please pop some questions into the Q&A. Let's make this a really interactive discussion. Actually, the first thing I thought, Alex, was it might be useful just to hear a little bit more about you and your research program and how you've got to this point, and why you decided to look at natural ventilation in this way.
Yeah, I mean, it's interesting. I think I started this work on my PhD, and when you start a PhD, you kind of start with this big defined question, right? That could kind of lead into anything. And so my background was mathematics, so I was used to the kind of fluid dynamics of these things, and looking at these from a kind of engineering perspective. But when we started to look at some of these infection risks and these naturally ventilated wards, we started to see some of these different spikes. And when we were using CO2 as these different measurements and thinking about whether our airflow was realistic, we started to see some of these patterns where this behavior was a bit transient and a bit sporadic. So that kind of posed the question to dive a bit deeper, really, to see what it was that was actually causing that behavior, and what governs the way that our contaminants that we breathe out in indoor environments move through some of these multi-zone spaces. I think there's a lot of consideration for single zones, but actually sometimes that long range transmission gets overlooked. And we saw through the pandemic that, especially some of the quarantine hotels and things like that, that you didn't actually have to be in contact with an infectious person to become infected. Just these shared environments, or entering a room after somebody else had been in there. So that kind of idea that these things stay in the air and move through the space, I think, is important.
Okay, interesting. Did you have a particular hypothesis around natural ventilation that you were trying to explore and tease out with this piece of work?
I think for us, we were interested to see whether there was particular weather conditions that actually drove some of this natural ventilation. And when we did this long range study, we couldn't kind of identify what, so we considered wind direction, wind speed, temperature, and pressure. And actually in this study, it was quite hard to identify which of those affected the natural ventilation in this way. But yeah, I think more generally, it was just about actually a lot of these spaces rely on natural ventilation, but that is out of our control. And so it was just that curiosity to see what's actually governing these, but also stripping it back from a modeling perspective so that we're only assessing that as well. Because these features actually get dominated if we start to consider different infectiousness of individuals and stuff like that, or transient occupancy, then these features start to become a bit more silent in the results, and so you actually miss some of these features. So the main study really here was just actually stripping everything back so that the only thing we were varying were those weather effects and natural ventilation to see what was actually going on under the surface.
So who would have thought that the shipping forecast may influence your risk of healthcare associated infection, right?
Yeah.
I mean, could it even be, we talk about seasonal variation in the risk of healthcare associated infection, and sometimes that's not obvious actually. Sometimes it goes the wrong way, and you might expect certain infections to be more common in the winter and they're more common in the summer. Could it have to do with atmospheric conditions and ventilation, an impact on ventilation rather than any other factor?
I think it plays a huge part. I think the other thing that we have to consider when we've got naturally ventilated spaces is the way that occupants react to external weather conditions as well. And so if you've got a space that relies heavily on natural ventilation, but it's a particularly cold day and you've got a ward of particularly vulnerable patients, they're not going to want those windows open. And so, how we behave, that isn't naturally affects the behavior that we have. We saw during the different lockdowns how, you know, infection was probably lower in the summer because we were all outside, spatially distanced, and getting all of that fresh air. Whereas actually in some of these indoor environments, then in the winter when we didn't want the windows open, then we started to see the increase in risk. And I know that other workers looked at the effects of kind of relative humidity on these infections and going into this kind of survival chemistry of some of these different pathogens in indoor environments as well, and how those different air quality features can start to influence that pathogen survival indoors.
Interesting. Okay, so we've got a couple of comments in the Q&A from Catherine and Lisa along similar lines, thinking about whether specific patient placement in the ward might be influenced by very, very local ventilation fluctuations. So before we get to those questions, I just wanted to ask a little bit more detail about that the assumptions that you use to find those conclusions, really. So how did you, what was your risk index that you used throughout the study, and how did you come to that?
So the risk index was essentially we took an average of kind of the prediction over different months. So we had a 6-month period and we split that down into 7 weeks. And so if you then take those kind of 7 weeks as an average of one another, you get this kind of probability of a particular number of infections. So you run a simulation multiple times, that gives you a risk index for a given week and a given weather forecast. And then you take that value and kind of divide it by the population, and that gives us an expectation of the average number of exposures from a given ward scenario, basically. So it's kind of like an average. It's a bit more like a percentage, but as a kind of 0 to 1 scale rather than 1 to 100 in that sense. So yeah, I mean, we make a lot of assumptions in that sense, and that's kind of the caveat with modeling, is that you have to get these things running and think about these kind of complex scenarios. Of course, we assume that the infectious person is present for 7 days, which, you know, may be realistic for some pathogens, but may not be for others. Again, you've got that kind of transient occupancy, which I think, you know, thinking about some of those questions coming about patient placement, again, if we've got an infector who's actually moving around the space and not stationary in one position, then that might start to affect the way that some of these features come to light as well. We did a previous study where we had a transient infector moving around the space, and we actually didn't see some of these sharp spikes and peaks, and that's because some of that other transient behavior was the more dominant feature. So there's kind of this balancing act with modeling where you have to make a reasonable amount of assumptions that the model's still realistic, but also thinking about what you're actually trying to show, because some of the different features can start to dominate those other factors that may be important or important for different people as well.
Okay, so thinking along the lines of sort of all models are wrong, but some are useful. Are you sufficiently confident that those zones and the risks attached to each zone in the ward, are they sufficiently constant with the changes in natural ventilation to start making decisions like, well, let's put the infector rather than by that window, let's put them in zone 10. So then that means that optimizes the reduction in the spread.
Yeah, I mean, I think I'm at danger of sounding like a politician and swerving kind of commitment to some of these, but you know, we have to caveat this with weather conditions change, right? So we use a typical weather file here. So this is the weather file that we've used in this case was for 2021. So you can say yes, these airflows and weather conditions are accurate for that year. Obviously, that's a typical representation for maybe a month that you might use for the year after. But I mean, we're all experiencing this nice weather now in March, whereas I think last year we probably had snow, right? So we're going to get some different weather conditions that are going to lead to different airflow patterns. But one thing that I've seen consistently through this work is when we're using the same weather file, as you can see from the results I showed earlier, when we had the kind of natural ventilation versus the mechanical ventilation, it's still that bottom area of the hospital ward that was experiencing the higher levels of risk. So you can start to make decisions about that, and actually, you know, wind flow, wind direction starts to affect the same wards. Obviously, the orientation of these buildings aren't changing. So when you experience a predominantly westerly wind, you can expect the same wards to be affected as another day with westerly wind, for example. One of the other things that we did see in the ventilation rates was actually that I'm not sure if you remember the heat maps, but it was some of the zones with the highest extract ventilation through natural means that had some of the highest risk. And so one of the questions I started to think about was actually, is natural ventilation effective at moving pathogens through the space, but actually not as efficient at removing them? So in terms of effectiveness as a mitigation strategy, it might be effective at actually providing this contaminant transport and moving them to different zones, but not actually efficient in removing that risk from those zones. And that might start to play a part on how efficient other mitigation strategies are as well.
Okay, it's interesting, isn't it? Okay, so to try and pull together a few questions that are coming through, thinking about open windows and specific patient location, if you have an infector, are they better off by an open window or far away from an open window in terms of transmission risk? Can you generalize?
I don't think you can generalize. I
Okay.
don't think you can. Yeah, I think it depends very highly on it'll. I mean, we're looking at this ward, this is a particular orientation, so depend whether the hospital ward is on the other side as well. So
Yeah.
obviously most of these hospitals are kind of symmetric, so if you had it on the opposite side of the building, then
Yeah.
you'd expect to get the kind of opposite effect. So I
Yeah.
don't think you can give those generalized mitigation strategies of where to move people.
Yeah.
You can get an indication of how particular weather conditions may start to affect the risk on those wards.
Okay. you maybe couldn't envisage a scenario then when you say, oh, it's a westerly wind today.
Yeah.
We'll put Mr. Smith in this corner of the wall because he'll be safest there. I don't think it's going to work like that, is it?
No, no. And I think, this study was more about actually saying, let's make people aware of the fact that this natural ventilation is something that you can't be certain about. It's a natural phenomenon, right? We're not governing the weather conditions each day. And so it was less about actually predicting exact outbreak scenarios, but making, people who are making decisions about future hospital design, particularly, or
Yeah,
retrofit, aware that actually they should be considering external weather conditions. And also other modelers as well, because there's a lot of modeling studies that consider steady state weather conditions. So that's the weather conditions that aren't changing. They pick a set condition and say, right, that's what we're going to monitor this. But obviously then you lose all of those temperature differences between indoor and outdoors, and the different wind speeds and wind directions across different weeks. Obviously, the fact that we've got this kind of average representation of risk index through the heat map, that might change week by week, but this is kind of the average representation. So yeah, it's very difficult to predict. I wouldn't like to say that this is something that can be used in certainty, but it's certainly something that we can say, this is something we need to be cautious about and aware of as well, because this is something that we take for granted in building design, right? When you go into an indoor space, you don't think, as an IPC nurse, you're not thinking, should I open a window? Should I close a window? So it's that kind of challenge, isn't it? And I think actually just making people aware of this is a nice tool in itself.
I don't know. I don't know that's true anymore, Alex. I think before the pandemic that was true. I think now the infectious control community are thinking, let's get that window open.
Okay.
It was something that we were told to do by the government during the pandemic. It was one of the domains of the board assurance framework, is that we had to try and open windows where possible. So I actually think it is in the kind of professional discourse to try and get windows open to the extent possible. Okay, I just wanted to go back to that same question, but from the other way around. We talked about the infector and decided we couldn't be sure. What about a patient who's not shedding but is at risk of being exposed? Are they better off by an open window, or is it again it would depend on the scenario?
Yeah, I think, again, it would depend on the scenario, because
Okay.
if you've got a transient infector, for example, I mean, this study, like I said at the start, only looks at long range transmission, right? So if you've got an infectious person who's moving around a space, we can assume maybe they're a healthcare worker and they're moving between zone and zone, that long range transmission risk might vary for somebody, but then you start to take into account the close range transmission risk as well, which isn't considered here. So it might be all well and good having a patient placed in a really well ventilated room, so they're not going to get infected by somebody who's down the corridor because the wind's blowing in a different direction. But actually, when that infector is then stood over their bed
Yeah.
and doing patient care, then that starts to be a totally different scenario. So I think, yeah, it is really difficult to predict exact outcomes from modeling studies, of course.
Okay, good question from a Joma here, which is, did you include some kind of parameter around ward activity levels, both in terms of patient flow and in terms of staff movements into your model?
We didn't with this model, no. So we've done that previously. So we had another model that looked at an infector moving around the ward, and again that kind of became that dominant feature. This model, we didn't include those transient behaviors because we're kind of looking at that long range, I suppose, time average scenario where we assume that there is somebody in each of the beds and we've got a kind of full staffed rota, and just looking at those scenarios as a kind of as an idea, as a marker to where this would go. Of course, future studies, we are looking to kind of incorporate that transient behavior and see how dominant these effects stay when we have a transient infector who's moving around the space and moving into different zones. But I think the point of this was that we lost some of that when we started to have that transient behavior, because then that becomes the dominant feature, as we were saying.
Yeah.
If the infectious person then enters zone 1, then obviously zone 1 is at elevated risk naturally because there's an
Yeah,
infector in the room.
forget about the ventilation, right? If you've got
Yeah,
somebody shedding in zone 1, get out of zone 1.
exactly. Yeah.
Okay, so something you just said made me think around other transmission routes and how important those may be in terms of a moving infector, but also other transmission routes. Could you build into this model contact transmission through the air over a short distance and through the air over a long distance in the same model, or would that begin to become too congested and actually not pull out anything useful?
I think you definitely could, and I think, you know, as a modeler, this is the kind of thing that we do these studies for, right? Is to make somebody aware that these external conditions are a problem, and so that they should be considered in future models when we incorporate these all together. And so this model works in a two-phase process. So we have a kind of airflow simulation where we consider the weather, ventilation, and the way that it moves through the interzonal flows, and then we couple that with a kind of numerical model, which is like a coded mathematical model that then considers the way that the pathogen moves through the space. So there's loads of scope to actually start to couple some of these things together. It's quite difficult because you end up with an awful lot of stuff. You know, where do you stop when you start to use other different transmission routes as well? And then different things become important. So in this case, this isn't a computational fluid dynamics model. So this is what we would call a network-based ventilation model. And so it considers quite coarse, well-mixed zones, which is what you might have seen a lot through the pandemic, through things such as the Wells-Riley model. They consider zones as well-mixed. So they consider that within a single zone, so for example, within zone 1, it considers that the concentration of pathogen is the same throughout that whole zone, which obviously in reality is not true because it depends where that infectious person is situated. But then different things become important if you start to look at close range transmission, then things such as turbulent mixing and the way that the airflow is actually moving within that zone, thermal effects maybe from radiators or actual individuals, and how things are actually moving if you're moving beds and patients through rooms. These start to have a knock-on effect on the airflow. So it does get very complicated very quickly. And I think that's probably why you see a lot of studies that are isolated in different transmission routes. And then, of course, there's the touch transmission as well. So thinking about fomite transmission and touching infected surfaces and then touching mucous membranes, things like that. Yeah. So yes and no. Yes, it can be incorporated and should be incorporated, but it's very difficult in practice to kind of, it's complicated, computationally heavy once you start including a lot of these different features.
And I guess with a model, you risk overcomplicating it so that it becomes further from reality, ultimately. Okay, well, one more question from the audience, and then I have one to conclude with. So Lisa's asking, if you had a standalone HEPA filter unit, where would you put it, and do the risk maps help?
So I hope the risk maps do help. That would be nice. Where I would put it again is back to that question of uncertainty of weather conditions and ward location. I think that's a difficult question, but I think instead of thinking about the risk heat map, I would be thinking about the ventilation heat map and saying, okay, what zones are actually contributing to this average ward ventilation rate? Because as we saw with the blue heat map, that there were some zones that weren't benefiting from any ventilation at all and weren't contributing to that overall ventilation rate. So those would certainly be zones that I would focus on, zones that could benefit from more ventilation. You might look to put additional ventilation in zones where you know you have particularly vulnerable patients. That might be a sensible decision. But again, this is going to, highly depend on where that infectious person is. It's probably much easier if the infectious person is a patient stationary in a bed than a healthcare worker who's moving around with the HEPA filter to go and put it in a different room. But yeah, so I think that is a challenge. It's a difficult question to answer.
Okay. Well, I mean, whilst it would be great if patients stayed in their beds all the time, unfortunately, that's not reality. They need to get out, they need to exercise, and some of them are not very good at staying put. So yeah.
Yeah, of course, this shows my naivety to healthcare settings.
Yeah. The roving infector is something that we deal with regularly.
Right.
Okay, so last question, Alex, and then we'll let you go. So thinking about a hospital of the future, if you were to design a ventilation system for a new build, would any element involve natural ventilation, or would it be mechanical all the way?
Oh, you like your tough questions. I think that's really difficult because I've not done a study on kind of energy efficiency. I think if I was to summarize some kind of key points that would influence my decision, I think mechanical ventilation is good in the sense that it's a bit more consistent, right? But consistency also relies on maintenance. And so these systems we assume have to be well maintained. So that's a downfall with mechanical ventilation, is that we
Yeah.
think these systems are in place and working fine, but actually nobody's checked them in 12 months, or the filters are full of worse things than what might be available in the room at the time. But then there's also that energy efficiency thing, and that was what motivated the guidance from the NHS and HTMO3 to stay as natural ventilation, was thinking about, the energy consumption of running a mechanical ventilation system. I think there's a place for kind of hybrid. I think there's a place as we move towards smarter technologies to be able to switch between the two of those ventilation systems as well. I don't see a reason why that shouldn't be a possibility. But I think to pick one or the other is very difficult and would depend highly on the space as well. I think it's also important to remember that if you try and put a fully mechanically ventilated system inside an older hospital, and say you chose to shut off all of the natural means, that a lot of these hospitals over time have developed leakage points and points to the ambient environments that in many cases are contributing to these natural ventilation rates that we already see. And so actually limiting some of them is really difficult as well, and starts to change the way that we think about building design, but also I think building resilience as we move through time. Just because we put a ventilation system in, as we've shown with the guidance today, just because we put a preference for natural ventilation that worked in 1910 when I showed you that picture, that doesn't mean that it's still going to work today. And so actually we need to be flexible around the choices that we make to make sure that we're adapting to changing environments and changing guidance in some of these spaces.
Okay, thanks, Alex, and thank you for a fantastic session today. It's been really thought-provoking. As somebody said in the chat, we're going to get out the shipping forecast, we're going to get out our wind socks and maybe use those to help us make better decisions, but it's certainly food for thought. So thanks for joining us. It's been great. So the next Journal Club's in a couple of weeks' time. I'll be leading a session on Candida zyma auris, previously known as Candida auris, and the emerging threat that presents. And then a couple of weeks after that, in early April, we'll be collaborating with the Infection Prevention Society to do a journal club with them, along with Prof. Jackie Prieto and Dr. Jude Robinson as well will be joining us that day. You can visit the website for the schedule for future events or the YouTube channel for recording of past events. Thanks to IPC Partners for hosting today, and we hope to see you again at the next Journal Club. Thank you. Goodbye.